Hello, everyone. Welcome to this MOF 2024 webinar. So I'm Jiang at National University of Singapore. Today, we are very excited to have top science Professor Banglin Chen to give the lectures on his journey to MOFs and HOFs. So before his lecture, I'd like to introduce you briefly. Professor Banglin Chen received his BS and MS degrees in chemistry from Zhejiang University in China, and his PhD from the National University of Singapore. He has been working at the University of Michigan, Cornell University, Louisiana State University during 2000 to 2003, University of Texas at Rio Grande Valley during 2003 to 2009, and the University of Texas at San Antonio during 2009 to 2023. Now he is a university distinguished chair professor at Fujian Normal University and the Zhejiang Normal University, working on multifunctional MOF, HOF, and HOF materials. He has published more than 450 peer-reviewed articles, including Science, Nature Materials, Nature Energy, Nature Chemistry, and JACS and many other prestigious journals. He receives the citation over 80,000 times with an H index of 131 based on the Google score, and issued 18 patents. He is a fellow of American Association for the Advance of Science, a fellow of Royal Society of Chemistry, and a foreign fellow of European Academy of Sciences. In 2011, Dr. Chen was ranked as the top 15 chemists over the past decade based on the citation impact score by the Thomas Lewis. During 2014 to 2023, he was chosen annually as a highly cited researcher in chemistry field by the Qualified Analytics. In November 2018, he received the Humboldt Prize. Today's talk is on our journey of exploring multifunctional metal-organic framework and hydrogen-bonded organic framework materials. So please, Professor Banglin Chen.
Thank you, Donglin, for hosting the webinar and introduction. Also, thank you, MOF 2024 program chair, and for the organization and the invitation. So today, I will be very happy to share my story, basically the story of explore multifunctional metal organic framework and hydrogen bonded organic framework materials. As Donglin introduced at the beginning, I finished my bachelor degree in 1985 and finished a master degree in 1998 and worked 7 years at the Zhejiang Normal University before I continue my PhD studies at the National University of Singapore. So it means that I spent 10 years before I continue PhD studies. So it's quite late. So in 1995, the time I joined National University of Singapore, and that time the facility at the NUS was not so good. But actually, I brought one organic linkers that is sulfine 2,5-dicarboxylate to synthesize a lot of different kind of compound, because my supervisor, MOF Conform, asked me to construct a sulfine-based compound. And one of the structures showing here, that is a coordination polymer. Here is a 2 zinc pedal bridged by solving to 5-dicarboxylate to form 2-dimensional structure. And as I mentioned, it's a coordination polymer. And at that time, research on coordination polymer was quite popular. I show you some example. For example, the Mike Sawalatkos compound, and showing that actually in his title mentioning the porous solid. And the Chinese scientist Xiaoming Chen actually used the different kind of organic linker to construct this kind of framework structures. There were also several other scientists all over the world working on this type of coordination polymers like Robertson, Tiny, Martin Shalondo, and Fujita, etc. And frankly speaking, I didn't understand and didn't know what this kind of coordination polymer will be useful and why this kind of topic was kind of hot that time. And in fact, in 1995, Omayaki used a term called the macroporous metal organic framework, and Susumu Kitagawa also used the term framework, and in fact for the small molecule capture. When we talk about the coordination polymers and the metal organic framework, the term coordination polymer was from the chemistry point of view, indicating the polymer nature. Well, basically, the term framework is a kind of architecture term, means the stability of the frame. And to a certain extent, because Professor Yaki has the background of solid-state chemistry, and we know that the framework, the term framework has been used in zeolite material quite a long time ago, I think. So this term is from the stability of framework and from solid-state chemistry science point of view. So the work motivated me to apply for postdoc job to join the Dr. Yagi's group is that one, is that work. If we compare these two structures, the structure are kind of similar, means the topology is the same. And frankly speaking, at that time, I didn't realize how important is this gas adsorption isomer. And the concept to make use of coordination polymer as a porous material to a certain extent has been proposed some time ago, but no permanent porosity is then established by gas adsorption isotherm has been established there. So the more time we spend on this topic, the more important of this paper, because this is the first example showing the material indeed has permanent porosities. So at Dr. Yagi's lab, I was assigned the project one on covalent organic framework. So you will know that the term was a long time proposed already by Dr. Yagi. The objective of this project is to construct single crystals with open space and porosity. And indeed, I tried a lot of different kind of coupling and condensation methodologies, try to synthesize such core material. And but apparently, I failed to get single crystal which are large enough to be characterized by single X-ray diffraction studies. And interestingly, I think last week in Science, Professor Wang Wei published this paper called Fast Growth of Single Crystal Covalent Organic Framework for Laboratory X-ray Diffraction. And even in that case, a special case, the shift-based condensation use reversible conditions to try to get a larger crystal. So, fortunately, Dr. Yagi also allowed me to develop a second project, which I more comfortable is metal organic framework. So I show you two work during his lab. One is I use this adamantine tetracarboxylate as a linker with copper pad wheel, and the structure, of course, is predictable. It's platinum sulfide structure. The most important thing is that once we remove all these terminal water molecules, the crystal is still stable, and all the terminal water molecule can be removed, so have we call the open middle size. And conceptually, this was very important. And over the last 2 years, Dr. Chen Ma developed this material for different kind of gas separations. The second work is to develop a very simple thermal synthesis methodology to synthesize MOF single crystal with a very short period of time, typically 1 day, because before that, the synthesis of MOF was quite complicated, typically by diffusion. The first very famous MOF 5 was synthesized by the diffusion method by deplanation of bicarboxylate. So the yield was low and typically has a different kind of mixture. So, but with this very simple thermal synthesis, very simple, and simple can be very pure. Secondly, this work means that we can use quite a large organic linker. We still be able to construct a MOF material with very large pore space, but still stable. And also from the last copper ATC MOF 11 and this MOF 14 shows that under certain condition, if we can generate this pedal wheel cluster and a different organic link shape, basically the structure topology are predictable. And nowadays we call it reticular chemistry. Such a reticular chemistry has not been realized in traditional solid state chemistry, because solid state chemistry has been long time been criticized by other organic chemistry because there was not much regional design strategy, and during the synthesis, even the thermal synthesis, we don't know what's going on. However, for this MOF chemistry, indeed, there exist certain degrees of regional design called reticular chemistry, and this work was highlighted by Dr. Philly, and in his title is very interesting, The Simplicity of the Complexity, Rational Design of Giant Pores. I continue my postdoc training at Cornell University and Louisiana State University for a very short period of time. At Cornell, we plan to develop conducting framework material, try to control the piping. We did make a little bit of progress. And at Louisiana State, we use metal ligand to generate we call the mixed metal organic framework, means that we can immobilize different metal size into the framework. And I started my independent academic career at UT Rio Grande Valley in 2003. And we didn't have any advanced facilities. So that during the summer of 2004, I went back to Omar Yagi's lab at Michigan to have one of our first MOF material exam for the hydrogen gas storage. And you will see that this pitch carboxylate with pad wheel, the structure is niobium oxide structure, predictable. And again, we can also generate open metal side for hydrogen gas storage. At the same time, Martin Shalondo published their work of this MOF as well. And obviously, we can use large different kind of tetracarboxylate acid to synthesize isostructure MOF material, and then their pore space and surface areas can be maximized for their hydrogen storage, very high hydrogen storage capacity at low temperature of 77 K and high pressure. But under this low temperature, 77 K and 100 bar, there is a limitation because we still need low temperature, which means we need to cool down, use liquid nitrogen for hydrogen storage. And recently, we realized that for traditional MOF material, there's a limitation for their hydrogen capacities. We realized that for different type of MOF material, one type is this kind of isolated cage. So there exists a pore surface on this cage. Another one is a channel, the porous material. And you will understand that for this type of porous material, because the cage has more interaction with the surface, and if this is a hydrogen gas molecule, will have a little bit stronger interaction with the hydrogen molecule. So the hydrogen occupancy means the degrees to the saturated hydrogen supposed to be 100% will be higher than those MOF material with linear channel. And we realize that this empirical formula is much better than original empirical formula with linear relationship. So once we know the porosity, pore volume, we are able to estimate their performance for hydrogen storage. And you will see that traditional MOF have this maximum storage capacity. So the challenge is how to enhance the hydrogen interaction with the MOF material. And because of that, because the higher the interaction with hydrogen means higher temperature for hydrogen storage. Because of that, we thought we might use metal ligand because this metal size might potentially have stronger interaction with hydrogen molecule. and we construct this mixed metal organic framework, and indeed, the interaction with hydrogen is higher, over 12 kilojoule per mole, and typically those MOF material only have 7 to 8 kilojoule per mole entropy. Furthermore, these materials show kinetic separation for hydrogen and deuterium, but still very challenging to further enhance the interaction of MOF material with hydrogen. And recently, the group from Jeff Long made some progress to have even higher hydrogen interaction. And so the open middle side apparently will be useful for other gas storage. For example, we realize high density of open middle size will have stronger interaction with acetylene, and then the acetylene uptake will be very high because acetylene storage needs to be realized at low pressure and room temperature because of its explosive nature. And we clearly realize this open metal size is a primary binding size of the acetylene. And because of that, we further synthesize MOF 74 series, because the MOF 74 series apparently have the highest open metal size, and in cobalt, MOF 74 has highest acetylene storage capacity. And of course, the MOF material will be also very promising for methane storage. And we also realize the empirical formula for this methane storage capacity means that we are able to calculate from the pore volume the methane storage capacity. And because nowadays, once we know the crystal structure, we can estimate pore surface and pore volume, then we can calculate methane storage capacity, so significantly reduce our time and facilitate screening to discover high performance methane storage material. And you will see the match calculate experimental one match quite well. And during our studies, we kind of unexpected that change from benzene to this pyrimidine here to nitrogen will have a little bit stronger interaction with methane. So the methane storage are quite significantly improved. And this is because the stronger interaction and rotation, low energy bar for the rotation. So this is, that time is a record methane storage capacity. Again, we realize the methane storage empirical formula under different conditions. You will see that at 65 bar and low temperature, this is presumably the maximum storage capacity and still below the Department of Energy's target. So we're wondering if we lower down the temperature a little bit to 0 degrees, then the uptake can be significantly improved another level. So, and you will see adsorption, desorption is an exothermal process, and we still need to control the temperature. Okay, now we turn to the next part. This is our main part on the gas separations. And we synthesize this material, and the pore is on 4 angstrom, and we realize that these 4 angstrom can exactly recognize the linear part of alkene. So we pack the column for GC separation, so can separate natural gas and also hexene and pentene and isomer. The mechanism is very simple. the longer the linear part of alkene, the longer in depth the recognition with this porous material, and then the stronger interaction, the longer retention time. So that work motivates us to study MOF material for gas separation, because as a reticular chemistry, we can easily tune the pore size for sieving separation. And sieving means the material can allow small gas molecule to go through the channel while block the a little bit larger molecule. Secondly, on the pore surface, we can easily introduce different kind of specific size, like Lewis acidic size or basic size or open metal size, for specific recognition of one gas molecule over another gas molecule. And also we can make use both function and develop functional gas separation material. Furthermore, the MOF material has certain degrees of flexibility, dynamic. Then we can use different temperature and pressure to optimize separation performance. So it is a very powerful platform for gas separation and purification. So I show you several examples. And this is one example using same organic linker, but a different payload. So the structure isostructure, the pore surface systematically changed, tuned, and this exactly can show in sieving separation. However, this interaction with this gas molecule are kind of weak, which means separation only realized at a low temperature. And ideal one is for separation at a room temperature. So we were kind of first group to examine kind of large scale separation. Here is the hexane isomer. So at a room temperature, this hexane isomer can be well separated. And during our studies, we accidentally realized a mixed MOF material show quite good separation performance for acetylene and ethylene. And in this example, this separation selectivity is quite good. And in another example, as mentioned, the MOF 74 can take up a large amount of acetylene. However, this also takes quite a large amount of ethylene as well. But this uptake is quite high, so here the selectivity is not good. This is another example for this separation. So ideal one is to have both high uptake and high selectivity. That we call the trade-off, because typically high uptake will sacrifice low selectivity, and high selectivity will sacrifice high uptake. And our breakthrough for MOF material for gas separation is this work, and kind of accidentally discovered by my postdoc, now a professor at Fujian Normal University. And the material we call UTS 16, you will see that compared with a large amount of different kind of MOF material, this material very unique. Quite high uptake for carbon dioxide capture, and an atmosphere and room temperature. However, also moderate entropy. This is good for regeneration. And only one example is MOF 74, and this one typically is considered to have chemical bonding with carbon dioxide. So that we need to figure out the mechanism why this material is so unique for carbon dioxide capture. So structure study indicated that this pore is suitable, is about 4.4 angstrom, 4.5 angstrom, exactly can capture a cluster of 4 carbon dioxide. Furthermore, the terminal water molecule initiate the primary binding site with carbon dioxide, so we call the dual functionality. So nowadays, dual functionality or triple functionality are very powerful strategies to developing gas separation MOF material. And sometime in 2015, Huabing and Mike contacted me showing their result on this MOF material for this ethylene separation. You will see that the mechanism is the same as we discovered in carbon dioxide material. So you will see suitable pore size exactly capture 4 acetylene molecule, and the terminal fluoride has a specific site for a little bit stronger recognition with acetylene molecule. So resolve this trade-off of have a high uptake and high selectivity, and this certainly is ideal material for these acetylene and ethylene separations. Not only that, the reticular chemistry allow us use even shorter organic linker. So you hear the principal one is carbon-carbon triple bond linear. The linker is a little bit longer than this. So using this shorter organic linker, you will see that the pore size will become a little bit smaller. Now can completely block ethylene, but still allow excess of acetylene. So now you will see that the acetylene uptake not much change, but the ethylene uptake is significantly reduced. So the purity and the productivity of core we can maximize. So this is another very powerful example indicating how reticular chemistry we can tune their separation performance. And we also kind of further realize flexible, robust, and at that time not well examined for gas separations as well, indicating the first example of MOF material for propene and propane separations. And again, we can make use of reticular chemistry to systematically tune the pore to maximize this propene and propylene separation. However, you will see that most MOF material are kind of flexible. And flexible means, for example, in that case, under a little bit high temperature, the pore space will be open to take up this propylene. And this co-adsorption is not good because it will affect the purity of the productivity of separating performance. Although this is quite good compared. And this is another breakthrough for our studies of MOF material for gas separation. And I should mention that this material, the structure, was reported a long time ago, almost about 1 decade before the establishment of MOF chemistry. However, this material shows unbelievably unusual sieving separations of acetylene and acetylene, so very high sieving separation. And I would like to thank you, review, who point out that this is because of the rigidity of the framework, and this the square acid there's a limitation for rotation which fix this framework and make this framework rigid. Furthermore, that material is very stable in water because it can be synthesized in water and also can be synthesized by chemistry. And so in large scale, and this is a very promising material for true gas separations. This work highlighted by Hoge in Nature Materials. And this is another scientific example. We can make use of this functional peroxide for their stronger interaction with methane. So this ethylene and ethylene can separate in high purity. Of course, this material is not so stable. And we can also, you will see, using different kind of node, metal containing natter, significantly improve the sieving separation performance for propylene and propane, and the separation performance much better. And we also develop other materials, for example, for acetylene carbon dioxide separation, by sieving separation, very good sieving separation. And we can also use less amount of organic linker for this separation. And nowadays, we can even use still porous material, but without any organic linker for carbon dioxide acetylene separations. And so now you will witness the science development on coordination chemistry to coordination polymer, metal organic framework, and then here to back to the traditional porous material. We hopefully can save the cost of organic linker, and also this material is kind of stable. And for time being, I certainly introduce our collaboration with several groups. One group is from the Zhejiang University Chen's lab. We pioneering the research on sensing and light emitting material and sensing thermometers, and also the nonlinear optical material to make use of the pore space for this encapsulation of dimolecule, and furthermore for their lasing, two-pound lasing function, and in fact even for the called polar lasing. So polar lasing leads the dimolecule exactly along this pore space because the fitness, and during the morphosynthesis put this dimolecule, and they show one directional lasing functions. And with Jiang, we work together on a very high proton conducting material, even under high humidity conditions. And with Yingwei is a micro metal organelle single crystal, because this large pore space of about 500 nanometer will facilitate the diffusion, because the micropore will limit the diffusion. So with this hierarchical pores will be quite useful for their industrial application. So overall, with different strategies, rational tune the pore space of different recognition, functional side. We can even develop a traditional coordination polymer, even without porosity, still can developing functional material, and we make use the pore space for different kind of recognition. So platform, MOF a very powerful platform for developing different kind of functional material. Nowadays, even enzyme, right, and metal, a single metal atom for catalysis. So very platform. Now, second part, I briefly talk about this hydrogen-bonded organic framework, and the concept of making use of HOF material, basically just the organic compound, for porous material conceptually was proposed almost at the same time with MOF chemistry, but no much progress. So sometime, I think in 2010, I asked my postdoc to synthesize an old material synthesized by Jiang West, published in JACS 1997, and we realized the first examples of HOF material with permanent porosity, and furthermore, the material show high sieving selectivity. So that motivates us develop a different kind of HOF material. For example, this for high chiral separations, and the separation performance actually is quite good. And for different kind of gas separation, acetylene, carbon dioxide, and also carbon dioxide capture. However, for this kind of organic linker, typically it will form different kind of isomer, and also synthesis comparatively is not so straightforward. So we have been wondering use very famous carboxylate acid to construct HOF material. And furthermore, this kind of carboxylate easily form this kind of dimer. So the HOF structure are kind of predictable. And gradually we made some progress. I show you several examples. In one example, this you will see this dimer, and the structure is kind of stable. The material show quite good performance for ethylene and ethene separations. And this we can further optimize the pore space. Again, this is dimer, and here showing triple interpenetration, and then the performance can be further maximized. Actually, very good separation performance. You will see even better than the one we published in Science for MOF material. And also we can use this kind of HOF material, use a luminescent optical active organic linker for their sensing application, sensing for aniline sensing function. And recently, my former postdoc at Fudan University developed this structure. Again, it's a dimer, and use this organic linker. The pore space is smaller, and then even at a low time under low pressure ammonia concentration, the material take a large amount of ammonia, and this framework and this ammonia recognition can be reversible. So this very amazing material for ammonia capture. And unbelievably, and even without our imagination, that we can even use this kind of very simple organic linker with cyanide. And typically, no one will realize this. Even use this cyanide compound, we are able to stabilize the framework. And in fact, this framework is very stable because of the this here, the interpenetration, and also the pi-pi interactions, although the hydrogen bonding are comparatively weak. Furthermore, the material show a flexible and robust and get a separation performance. And when we increase the temperature, the uptake of ethylene decreases slightly. However, the uptake of ethylene significantly decreases, and in that case, the C-fin separation performance is unbelievably good. So if at moderate temperature, the high temperature, we are able to purify to get a high purity of ethylene. So this is very goodism. Compared with MOF material, the good things for HOF is we can easily recrystallize the organic compound. So we can reuse the organic compound again and again. That will significantly reduce the cost of the material for future application, because it's very, very difficult for us to recover organic linker and recover MOF material. So this is a uniqueness. And also this material can even be utilized for the separations of propene and propene, and even the four components of ethylene, ethene, and propane can be separated. So it's another example. So overall, nowadays, this HOF chemistry now become a hot topic as well, and we invited to write several review articles in this topic. And I'm pretty sure, particularly nowadays, for their application in biochemistry and biomedicine, and our collaborator made some significant progress as well for biomedicine. So with that, I will thank you a lot of collaborators, and I made a lot of friends over the world, and my former my collaborator, my former student collaborator, and postdoc and visiting scientists in our group. With that, I will thank you for your attention and happy to answer your questions.
So thank you very much, Banglin, for your very nice talk, exciting, bring us new chemistry with stimulating. So now the lecture is open for questions. So actually we have a lot of questions in the QA corner. Banglin, can you see the QA corner?
Oh, I thought you will pick up some. I was told you pick up some, and yeah, you just pick up some of the question, and because
Okay, okay.
to follow immediately.
One question is to ask how to control porosity of the curve and which model is better for calculating the surface area and porosity of MOF.
A MOF or HOF?
MOF.
A MOF.
Yeah.
MOF. A MOF comparatively much straightforward because the most popular one is the pedal wheel, right? And the second one is the octahedral zinc 4 oxygen, and another one is the UIO series. So they are
Yeah.
not very popular. So this with the reticular chemistry, and sometimes of course penetration will happen. And in
Yeah.
terms of program, the question about the program for surface area estimation. What the question? Another question?
Another question is for the model to calculate the porosity. What
Uh,
kind of model you use? Yeah.
the model uh, that one I forgot it, but it is
Mm,
very popular. You need to check physical uh, chemistry like a snare, landing snare, and I think they already have some program. If
mm,
I'm not sure if a Material Studio maybe so able to provide some accessible pole volume, something like that, you know?
mm,
Yeah.
yeah. Yeah. So another question is, could you give a comment on the comparison of gas separation using MOF powders with MOF membranes? Which one is better or more promising?
Oh, let's say, yeah, both have a different kind of advantage and disadvantage. I think depend on different situation and also is on political situation. Of course, theoretical speaking, membrane because can have a large surface, largest area separation, so the costly will be better. But now the challenge here is how to make stable and large areas membrane is challenging. It's very challenging because easily broken. The membrane is easily broken. And in terms of bulking material for breakthrough, the fixed bed separation, we need to figure out some other mechanical issue. Still the period stability and other the diffusivity for the two applications. But there has been quite a lot of progress for the bulking material for column separation of gas. And I think the time will be coming very soon, very soon. For membrane separation, yes, not yet, because the membrane is still not so stable, I think.
Yeah. So one question is, most of the MOFs contain highly active metals such as copper, iron,
Mm.
but still they don't show comparable nanoenzyme-like activities. What could be its reason?
Oh, the enzyme one, because in the biological system, I think the pore will be much larger and also much flexible, and the environment will also be more complicated, I think. So right now, the MOF is still kind of simple platform, so it's still a little bit of away from to mimic to enzyme activities, I think.
Yeah, yeah. So besides the pore size, how do the ligands help in the carbon dioxide capture?
Oh, the ligand.
Yeah.
Ligand. So here, the carbon dioxide capture pretty much is still so two mechanisms. One is a sieving. So the ideal one is to have a small pore. We can allow access of carbon dioxide, but the nitrogen and the methane will be blocked. But those sieving material typically will have a small pore size. So which means the uptake will be not so high. So in order to develop this kind of high performance material, the ideal one will have small window and quite a suitable large pore space. So maybe use a pore space to take up a large amount of gas molecule and use these pore windows for the sieving separations.
Yeah.
And organic linker, of course, we know the amine will have a little bit stronger interaction with carbon dioxide on the organic part and organic part, yes. But it's still very challenging. You will see for carbon dioxide capture mentioned under 1 atmosphere and room temperature, and high pressure is okay, of course, because the high pore volume on surface, the material certainly can take a large amount of carbon dioxide. But a low pressure, room temperature is still a little bit challenging, but we are almost there. I think we are almost there.
So in relation to this question, also, one question is, what properties of ligand and metallic centers could be beneficial for efficient carbon dioxide capture and its possible reduction to value-added products?
That I cannot give a clear answer.
Yeah.
Cannot clear answer. That's the yeah, need a physical chemist input, and also I need a synthetic chemistry, and also we were still experimental scientist. Chemistry is still
Yes.
experimental science. We need to try.
Yeah.
So
Yes. Yeah. So for the gas adsorption, someone asked whether the defects in MOFs could enhance or decrease the gas adsorption.
again, sorry, once again, what question?
Ask the defects in MOFs, how they affect the gas adsorption, they enhance or they decrease adsorption behavior.
That hard to predict, because different kind of defect will have different effect, I think. So it's a no simple answer. I think in certain case might enhance, but in other cases maybe not, because we need a study the pore size distribution and how this kind of pore size defect distribution will affect the gas performance, and also different kind of gas we need a different kind of MOF material because their pore size are different. So it's not a simple case.
Yeah. And the next question is concern the preparation method. How do we prepare a flexible and robust MOF? Flexible and robust.
This so basically the rigidity and the stability and the dynamic based on the node and also the organic linker. So if the node are larger, like 8 connected node or 12 connected node, it's understandable that this kind of MOF material will be more robust. So if the node will be too little, only 2, and then it will be too flexible. So basically, we need to have a balance to make use of this node and organic. Same thing is for organic linker. So organic linker is more rigid, then the resulting MOF material will be more robust. So that's the case. So how to balance these two factors it's still we need we need to develop chemistry. And once we know some isotherm, we can have some clue, and then we can slightly make some modification and optimize the performance. I think recently, I think Dan Li and we can publish a paper in HES, chemical and biochemical engineering. Is a flexible MOF material, I think.
Yeah, that's great, I think. So next question is about the specific features of MOFs in energy storage. And so how MOF performs the energy storage? Either it's just like hydrogen storage process or not. So energy storage using MOF.
Because the energy storage is a very broad concept, but because a lot is energy, like acetylene is energy, methane is energy, hydrogen is energy, and hydrogen is still doubting challenge, as mentioned, because of the temperature. But the scientists need to face the challenge because we are scientists. Because in terms of this question, I asked Suzumu Kitagawa as well long time ago, and because he said we are scientists, we need engineering, we develop other parts. And at the beginning of morphochemistry, because Omayagi is my postdoc, I asked a question about the stability of morph material. He mentioned that as a scientist, we need to develop science first, and eventually some stable material, morph material come out. So could be.
Yeah. One question is related to the stability of MOFs. So I'm concerned about the stability of MOFs in suspensions. I have tried a couple times, but are not stable in suspension, and the efficiency is significantly reduced.
That depends on what type of morph material. It's true.
Exactly. Yeah.
It is very few percentage of morph are comparatively stable, but there are some morph material are stable. There's no doubt. So
yes, correct. And do morph porosity matter in gas separation application?
morph what matter?
Porosity.
Porosity. No need. Yeah, I didn't mention. In fact, morph material for gas separation typically have comparatively low porosity. The BET surface, I think, typically less than 1,000 square meters per gram. No need high porosity because gas molecules are small.
Yeah.
Those are 500, more than enough for gas separation. Yeah.
So MOFs are excellent in adsorption, storage, and transportation, but why its catalytic activities are quite low, such as degradation of organic pollutants.
Why rare? Not well examined. What rare?
The catalytic activity are quite low in degradation of organic pollutant.
That I don't know. I don't. Maybe like application not many, because applied research sometimes cannot lead to high quality papers. Maybe that is the reason, but I don't know.
Yeah. So there are some questions for HOF systems. So what are the main concerns that should be keep in mind while designing a luminescent materials using HOF? How does the choice of organic ligand affect this application?
Ligand effect. Ligand left? No much. because HOF comparatively, other than the carboxyl systems,
Yeah.
no much additional design because the interaction quite weak. Only the carboxyl case we are able to synthesize iso structure of material. I cannot have any clear answer that. But of course, the organic linker themselves need to be highly luminescent. I think certainly will help.
Mm. What temperature of HOF is reached to the break stability?
What the temperature to break stability? You mean
Become unstable. I mean.
oh, that basically stability organic linker. So because at like 250 degrees, sometimes the organic linker will decompose. So
Yeah.
basically can be stable at that temperature. 250 should be
So
okay.
yeah. What's the most promising application for MOFs and HOFs in your opinion, and why?
Oh, of course. I think
Yeah.
for me, of course, more for gas separation and purification, very promising, and even for carbon dioxide capture, and for water harvesting, and for HOF, gas separation as well, and particularly for medical application, because the interaction are
Yeah.
quite big, and under weaker stimulus the structure can change and recognize different kind of drug and to deliver into the cell and for different kind of treatment. These will be because organic compound, pure organic compound, more compatible with the organic
Yeah.
system. So that will
Yeah.
be very promising.
Yeah. So next question is concerned with the HOF system. If the nitro group based hydrogen bonding frameworks are very weak, how stable it is, and how about its recycling property in gas separation?
Oh, that's very stable. The water, even acidic condition and basic condition, still stable. And the 250 is still very stable. So it's beyond our imagination. Because here, the weak interaction, but a lot of different kind of weak interaction collectively inform the structure. So this HOF material is true uh, uh, promising material, true promising material.
Yeah.
Yeah.
And one question is why it is difficult to design MOF and compare the properties, especially adsorption and catalysis via computational method.
Computational method for prediction of gas separation and storage performance is quite good, I think.
Yeah.
And for catalysis, I think is quite complicated. So nowadays, I cannot make any comment on this. I don't know.
Yeah.
Yes,
Yeah.
catalysis is still a little bit magic to me.
Yeah. Okay. So we are following protocols report well-known journals such as JAX, Nature, but we do not get the desired product. Should we go for modifications in the synthetic routes?
What's the question? It's about.
Uh, as question, they follow the protocols reported ones, but they cannot get the desired compounds or MOFs. Should we go for modifications in the synthetic routes?
That I think I suggest you contact the author, original author directly. Like the
Yeah,
scientific community is okay to ask a question. So
yeah.
why you cannot repeat?
Uh,
Because it's not straightforward.
yeah. And okay, the BT surface area of the MOF material prepared bore milling using metal oxide as the metal source is much smaller compared to that obtained by solution-based methods. What could be the reason for this difference? This is very specific questions.
I didn't get it clearly. I didn't.
So the BT surface area of the MOFs prepared by ball milling method
Oh,
or by the solution method, they are different. The ball milling method is much smaller. So what's the reason for this difference?
solution method. There's no
Mm.
BT typically use a nitrogen gas isotherm.
I mean the material, maybe they ask for the materials, different method for preparation of MOFs using the solid state method
Oh,
or solution
oh,
method.
That one depend. I think typically because solution based synthesize the material will be comparatively pure comparatively, and the
Yeah.
solid state synthesized by mechanical chemistry synthesis sometimes maybe have a certain degree porosity, and typically I think the pure
Yeah.
one of course will have a higher porosity. I think.
Okay. Okay. But still, we have a question concerns stability. How to increase MOF stability in suspensions?
Suspension.
Yeah.
The suspension, I think some kind of coating, maybe polymer coating, missile formation will be useful, I think. I think a Chinese scientist, one ball, use some kind of polymer to protect some. So hybrid material will be another strategy. Hybrid
Okay.
material with more
Yeah.
together.
Good. So let me have the last question, okay?
Mm.
So I read the comment for you. Hi, Professor. Thank you for your wonderful and inspiring talk. I amazed by how many groups you collaborate. Do you have any suggestion for a postdoc to build up such kind of networks?
Postdoc, postdoc, postdoc is because only when you are independent and then you have freedom to collaborate with anyone. So I think, and for me, and a postdoc, I think you still need to concentrate on your current project first before first. Of course, you can attend some conference for future preparation to have the network, and you will see that I didn't travel a lot, but most of the time when I travel around, I didn't tell you the story. And the 2007, our Jack's one on the hydrogen high entropy because I attended the Department of Energy panel, and I met the and then we work together to have the material examined. So, and I don't know. I think that because my philosophy is to make a friend, although we are scientists, and just work together to have fun, to have something interesting to work out. And my role also is to help students. I'm the mentor and a helper and supporter for my students. So a lot of people like to work with me together. So I think that's important.
Yeah, great. So that's all questions we received, and thank you very much for your very
Okay,
nice answers for a long time. Thank you very much for your very stimulating talk.
okay,
Really enjoyed it very much.
okay. Thank you, Tony. Thank you, so everyone.
So now the webinar is complete. I think, okay, thank you all the audience and Bonnie once again.
Okay, see you later.
Thank you. See you.